All right, let's get the review started. It's hard to say exactly how long this will take, but we'll plan on about an hour and a half. If you have to leave early, that's not a problem. It is being recorded, so it'll be on YouTube later today. This is the first one of these we've had because I had to miss the first one. So a couple things about this. The questions, hopefully some of you had a chance to look at them already. They are reflective of what's going to be on the exam. They're not exact exam questions, but the distribution of topics is identical, so you can get a feel for how many questions we're going to ask you about each chapter of the book that's being covered and on each topic as well. But obviously on the real exam, your questions are likely to be a little bit different, but again, the same topics. And while I'm going through these, you're welcome to stop me anytime with questions. This is for your benefit, not for mine, so I'm happy to stop and address any questions you have along the way. If it's about the specific problem I'm going over, or even if it's about something somewhat related to that that's a little bit different, I'm happy to take a pause and do that, so just don't be shy. All right, so I think with that, we'll just get into it. So as you'll see in this review, the first 5 questions or so deal with Chapter 4 material, which seems like forever ago now. So Chapter 4 was the chapter that, sort of the last of the molecular structure chapters that we started with, which deals with shapes of molecules and bonding and things of that sort. So this is going to be the stuff that's a little bit different, more qualitative, more conceptual in nature. So the first one deals with electron group arrangement and molecular geometry. So we're going to do that for the hypothetical anion VSEPR-. So anytime you're asked a question about geometry, shape, or anything like that, you need to start with a Lewis structure. So we'll review how to do that. That's technically a Chapter 3 topic, but it's going to be important for a lot of the stuff on this exam as well. So if we have VSEPR-, we have to count the valence electrons. So we have a selenium and we have a fluorine. And as a reminder, when we want to count valence electrons, we go to the periodic table and find out what group number it's in, and the group number directly tells us the number of valence electrons. So we have selenium and fluorine. Selenium is here. It's in group 6A of the periodic table, which means it has 6 valence electrons. Fluorine is over here in group 7A, so each fluorine will contribute 7 valence electrons. So before we draw a Lewis structure, we have to count how many electrons we're going to have. And so we have 1 selenium that's going to contribute 6 valence electrons, 3 fluorines that are going to contribute 7, and then anytime we have a positive or negative charge, we have to add or subtract additional electrons from that total. So this time we have a negative charge, VSEPR-, 1 minus charge, so we're going to add 1 more electron to account for the negative charge. So this ion here should have 28 valence electrons. So when we're drawing the Lewis structure, it's important that we have 28 valence electrons in there. The nice thing about VSEPR, when we're doing molecular shape or if we're trying to do hybridization, we don't have to get all of the details right about double bonds and formal charges and stuff like that, but it is important that we have the correct number of valence electrons and that we arrange them correctly around the central atom. So we're going to do that here for VSEPR-. We have selenium as our central atom, 3 single bonds to fluorine. And then we start by completing the octet of each fluorine, which requires us to add 6 more electrons to each one. Alright, so 3 octets have been completed. That's a total of 24 electrons, 3 times 8. That means we have 4 more left. Whenever we have extra electrons, they always go onto the central atom. So we're going to put 4 more electrons, or 2 pairs, onto the central atom. And this is going to still have a net negative charge. We can indicate that if we care. So we have this structure here. We don't have to draw any double bonds. Fluorine never gets double bonds, and like I said, it doesn't really matter for this type of problem anyway. The central atom has a complete octet, so everything looks fine. Actually, it goes beyond the octet. And so then if we want to write the AXE notation, if that's how you prefer to characterize things, the central atom selenium has 3 atoms bonded to it, so that's going to be X3, and then it has 2 lone pairs, 2 non-bonding pairs, so that's going to be E2. So the AXE notation is AX3E2, and the first part we're asking is the electron group arrangement. So electron group arrangement just depends on the number of total electron groups. It doesn't depend on whether they're atoms or lone pairs or any combination of those. So we just need to find the total number, which I call steric number. And that's going to be 3 plus 2. 3 atoms, 2 lone pairs is a steric number of 5. And so anytime you have a steric number of 5, no matter what combination of X's and E's you have, the electron group arrangement will be trigonal bipyramidal. So remember, with electron group arrangement, there's only 5 possibilities, and it depends on how many electron groups you have on the central atom. So the one that corresponds to 5 electron groups is trigonal bipyramidal. If it was 2 electron groups, it would be linear, 3 would be trigonal planar, 4 tetrahedral, 5 is trigonal bipyramidal, and 6 is octahedral. So it's those 5 basic electron group arrangements that we have that we can categorize all the shapes within, and at least for the types of stuff we'll be doing in this course. So that's our electron group arrangement. But then if we want to determine the molecular geometry, we have to also consider how many lone pairs we have on the central atom and just look at the shape that the atoms themselves make up. So if we have 5 electron groups, it's going to be trigonal bipyramidal, which is a triangle with 2 coming up the bottom and the top, selenium in the center. And so when we do the molecular geometry, remember we have to place the lone pairs first, and the lone pairs for any trigonal bipyramidal geometry are going to go onto the equatorial part, or onto the triangle, and then that leaves fluorines here, here, and here. And if you draw it in this way, you can clearly see what this shape is called. This is actually sideways, but this is what we call T-shaped. Alright, so there is a table in the notes back when we covered this that sort of summarizes all of the different AXE notations and the shapes that those correspond to. So we have to learn there's 2 different parameters to classify these geometries. There's electron group arrangement, and then there's molecular geometry, which are in many cases 2 different things when you have lone pairs involved. So the correct answer for this one would then be C, trigonal bipyramidal, and it's a T-shaped geometry. Okay, so any questions on this problem in particular, or VSEPR in general? Yeah?
When it comes to the AX3E2,
Yeah?
did it come from how many elements that are added onto it, and then E has to move along there?
Yes. Yeah, so this AXE, the X refers to how many atoms are bonded to the central atom. It doesn't matter whether they're singly, doubly, or triply bonded. It's just how many of them there are. And then E is the number of lone pairs. Remember that VSEPR stands for valence shell electron pair repulsion. So we always treat non-bonding electrons as pairs of electrons, and that counts as 1 electron group for each pair. Yep. So steric number is, I don't think our book uses that terminology. It's just the terminology that I was introduced to as a young whippersnapper. And steric number is just another way of saying the sum of these subscripts here, the number of X's plus the number of E's. So in this case it's 5 because it's 3 plus 2. And that's what defines the electron group arrangement, and that's also what defines hybridization. So it's an important parameter for both of those concepts. Yep.
In the little figure you drew, why wouldn't the fluorines be on like the vertex of the triangle?
So the reason for that is we want to put the lone pairs as far away from each other as possible. And it's not as intuitive with the trigonal bipyramidal geometry, but if you put a lone pair on the top or the bottom, it's going to be 90 degrees apart from one of the other lone pairs. And you always think of it as you place the lone pairs one at a time. So the first lone pair goes onto the triangle, and then the second one would have to go onto the triangle to be as far away from that one as possible, and then the third. So however you want to remember it, when you have trigonal bipyramidal electron group arrangements, however many lone pairs you have, they're going to go on the equatorial plane, and that's what gives those characteristic shapes that are associated with that electron group arrangement. Anything else? Yep. Well, so choice C just has them reversed. So we're looking for, the key word here is respectively. We're looking for the electron group arrangement first and then the geometry. So that's the geometry and then the electron group arrangement. Okay? Anything else? Yeah? Electron group arrangement. Okay, so we can summarize that real quick. It's a little bit annoying to insert blank pages on this, so I'll just try to do it at the top. All right, so if we have steric number of 2, that's going to be a linear electron group arrangement. 3 is trigonal planar. 4 is tetrahedral. 5 is trigonal bipyramidal. And 6, which is as high as we go, is octahedral. All right, so those are the 5 possibilities. Now keep in mind that within each of these, there are in many cases more than one molecular geometry associated with them. If you have 0 lone pairs, the molecular geometry and electron group arrangement are the same. They're given the same name. But when you have lone pairs involved, the molecular geometry will be something different than the electron group arrangement. And so, for example, within trigonal planar, if you have a lone pair, that's going to be a bent geometry. Tetrahedral, if you have one or two lone pairs, it's either going to be trigonal pyramidal or bent. So there's all these different possibilities within there that you want to make sure you're familiar with. And those are also summarized in the notes back then. Anything else? All right, moving on to the next one then. Here we're talking about polarity or dipole moment. So we want to know which of the following molecules have a non-zero dipole moment. And so this is kind of the types of questions we'll ask you. We're not going to really ask you to rank molecules in terms of polarity necessarily, but we want to ask you to determine which ones are or are not polar. And saying a non-zero dipole moment is just another way of saying that it's polar. So molecules that are polar have a dipole moment. Molecules that are non-polar have no dipole moment. So that's really the two characteristics, two categories we'll have. We want to know which of these are non-zero, which means they're polar. So again, for this type of problem, there's no shortcut. We have to be able to determine the Lewis structure and the molecular shape. And the molecular shape is going to allow us to determine whether it's polar or not. That said, there are some things we can remember about this that'll help us without having to keep all the possibilities straight in our head. So the first thing we can do is let's draw the three out. So we have, five. So let's do all five of them real quick. So I'm not going to go through all the details of the Lewis structure, but we should be able to do these fairly quickly now. So NF3 is going to be AX3E. So it's going to be trigonal pyramidal. So this is one of those that we sort of referred to last time. Now deciding whether it's polar or non-polar depends on what is determined by whether the individual dipole moments are canceled out or not. And anytime you have one lone pair, the molecule is going to be polar. So you don't have to think about it beyond that at all. So all of the molecular geometries that have one lone pair, you're going to have an imbalance of charge when you have polar bonds. So this is going to be polar because it has one lone pair. And you're not able to cancel out all of the dipoles when that's the situation. Okay, and then for BF3 is the next one. So this has two fewer valence electrons. Remember that boron is one of these weird ones that tends to form electron deficient compounds with only 6 valence electrons around boron. So you get this structure here. There's no lone pairs, and this is just AX3, which is trigonal planar. And another easy thing to remember when you're doing problems like this is if it has 0 lone pairs, and if all of the atoms around the central atom are the same, it's going to be nonpolar. So because this has no lone pairs and it just has fluorines bonded to the boron, this will be nonpolar. All of the boron-fluorine individual bond dipoles will cancel each other out in this arrangement. So one lone pair is always polar, 0 lone pairs is nonpolar. The ones that have something other than 0 and 1 lone pairs, you have to think about a little bit harder than that. The next one that's in the list is xenon difluoride, XEF2, a rare compound of xenon. And if we do the Lewis structure and the corresponding shape for this one, what we get is it's a trigonal bipyramidal electron group arrangement. And as the question we had last time, this time we have 3 lone pairs. So all 3 of them are going to go on the equatorial plane. Anytime you have lone pairs, they all go on the triangle. That leaves the fluorines up there and down there. And so in this situation, it's going to be, as we said, AX2E3. When you have 3 atoms, it's always going to be either linear or bent. This one's clearly linear. The 3 atoms are all arranged 180 degrees apart. So this is a linear molecule. And anytime you have a linear molecule, again, when the 2 outer atoms are the same, this would be a nonpolar arrangement as well. Okay, so anything that's linear with 2 identical X atoms, 2 identical outer atoms, is going to be nonpolar because the 2 bond dipoles cancel out. So far we have 1 that's polar, 2 that are nonpolar. All right, next one on the list is another xenon fluoride, XEF4. And so this one we're going to have 6 electron groups. So it's going to be octahedral electron group arrangement. 2 of those are lone pairs. So they go 180 degrees apart to get as far away from each other as possible. And then we have a square plane of fluorines. So this will be what we call square planar. So this problem also gives us a good survey of a lot of the molecular geometries that we had questions about in the last problem. And this one is another one that's nonpolar because we have two sets of bonds that are 180 degrees apart. So these two cancel each other out that are 180 degrees apart. These two, the dipoles cancel out, and in that you have 0 dipoles. So AX4E2, which has 2 lone pairs in a square planar arrangement, would be another one that gives us nonpolar type of situation. And then finally SF4, this one's 5 electron groups. One lone pair. So the lone pair goes anywhere we want on the triangle. So this is AX4E. This is the one that's always hard to remember a little bit. This is what we call seesaw. And as I showed in class, if you turn this over on its side, it rocks like a seesaw. But anyway, the point being it has one lone pair, and as I said earlier, anything that has one lone pair will be polar. So this is another one that's polar. And so what we have is we're looking for the non-zero dipole moments, which are the ones that are polar. So we have NF3 and SF4. So the two that have one lone pair are the two that are polar in this case. Okay, so that's going to be the correct answer there. So there's a few other possibilities that weren't covered by this problem, but with these 5 examples, we've seen a lot of them. And the 2 easy things to remember are 0 lone pairs, it's going to be a nonpolar geometry, and if you have 1 lone pair, it's going to be polar. Okay, and then the ones that have 2 or 3 lone pairs, you have to think about a little bit harder than that, but most of them, if you know the shape and you can look at the shape, it's pretty obvious. Any questions on this topic? Okay. And again, if anything comes up later, just come back to this, no big deal. Finally, the next topic we're going to get to in what's referred to as the localized bonding model or valence bond theory is hybridization. And so this is the idea. It's conceptually a little bit difficult to wrap your head around, but it's in order to form all these different shapes that we have, the atomic orbitals on the central atom have to mix with each other to make new orbitals that are arranged in the correct way. So if we just had atomic orbitals, just sp orbitals primarily on the central atom, those would have to be 90 degrees apart because the p orbitals are all, remember, px, py, and pz. Hybridization allows us to then explain why we're able to form all these different shapes. So we're going to go back to the ion that we did in the first problem, SCF3, and determine what its hybridization is. So if we had started at the beginning of this problem, we would still have to determine the correct electron group arrangement, or at least the steric number as I referred to before. As we already saw on problem 1, so we can save a little bit of time here, SCF3 minus we saw was AX3E2. And then for hybridization, all that matters is the total number of electron groups. Once again, it doesn't matter how many of them are atoms in lone pairs. It doesn't matter whether the atoms are singly or doubly or triply bonded. It's just how many of them there are that's important. So it's that key parameter that we call steric number, which in this case is 5, 3 plus 2. And when you have 5 electron groups, you need to hybridize 5 orbitals to be able to make bonds to those. And so the way we do this is every central atom is going to have an s orbital. It's going to have 3 p orbitals, and whenever you go beyond 4 electron groups, you have the possibility of also using up to 2 d orbitals for hybridization. So those are the individual atomic orbitals that we hybridize, and if we need 5 of them, we just take the first 5 in this list. Okay, 1, 2, 3, 4, 5 makes it sp3d. Okay? So it's sp3d hybridization because there's 5 electron groups, so we hybridize 5 orbitals. All right? And so that's going to be, the correct answer would be C. Keep in mind we could also write this as dsp3. It might show up that way on some of the test questions. Those mean the same thing. The ordering doesn't change anything. It's just that there's 5 electron groups, so you hybridize those 5 orbitals. So what you need then, as I said, for determining hybridization, all you need to know is the number of electron groups. And so we can run through quickly all of the possibilities, which again, there's going to be 2 through 6 electron groups in all of the molecules that we'll ask you to consider. And by knowing the number of electron groups, which again, you have to count the number of atoms and the number of lone pairs, both of those together, you can determine the hybridization just by knowing the number of electron groups. So for 2 electron groups, we hybridize 2 orbitals, which is sp. For 3 electron groups, we hybridize 3 orbitals, which is sp2. For 4, we have to hybridize 4 orbitals, which is sp3. After we go through sp3, we have to start using d orbitals, as we saw, 5 electron groups gives us sp3d, and then the highest we would go is 6 electron groups, which we have to hybridize a second d orbital to give a total of 6. So if all we're asking you to do is find what the hybridization is, which is most often what the case is going to be, you just have to count electron groups and correlate it to the hybridization. Questions on this one, or hybridization in general? All right, good. On to number 4. All right, so then number 4 is the next type of bonding theory that we deal with, which is molecular orbital theory. Now, this is the one that's theoretically the most complex. If we were to do it, mathematically, it's based on quantum theory, so it's quite ridiculous from a mathematical standpoint. And also, if we were to do it for any complicated molecules, it becomes really tough as well. So for molecular orbital theory, we just expect you to know how to do it for diatomic molecules that have just 2 atoms. Typically, they're homonuclear diatomics, which means they have 2 of the same atom in them. And we just want you to understand a few of the basic principles of molecular orbital theory, and then also how to use molecular orbital theory to make predictions about bonding and electronic structure. So as I sort of have here on the review, and this is going to be pretty representative of the exam that you're likely to have, again, there's some randomness in terms of what questions you get. But in general, you're going to have one question like this one that's kind of on the conceptual nature of molecular orbital theory, or some of the theoretical aspects of it. And then the second question is more of a practical one where we asked you to draw an orbital diagram and answer some question about the molecule. So this first one here, according to molecular orbital theory, which of the following will increase the bond order in a diatomic molecule? So we have to remember that whenever we form molecular orbitals, whenever 2 atomic orbitals mix with each other, you're going to get one orbital that's bonding, which is lower in energy, one orbital that's anti-bonding, that's higher in energy, and then you add electrons to those from lowest to highest energy, however many electrons you have. And so if we're looking for an increase in the bond order, remember that we have an equation for bond order that comes from molecular orbital theory, a pretty simple one, which is 1/2 times the number of bonding electrons, so it's the number of electrons that reside in bonding orbitals, minus the number of electrons that are in anti-bonding orbitals, so we can think about this either mathematically or conceptually. So conceptually, the idea is that when you add an electron to a bonding orbital, remember the bonding orbital has electron density between the nuclei, and that's going to result in strengthening the bond. So every time you populate a bonding orbital, you're making the bond stronger, or you're increasing the bond order. And then every time you populate an anti-bonding orbital, you're populating an orbital that has electron density outside of the nuclei, and that contributes to weakening the bond or lowering the bond order. So that's kind of the concept behind it, and mathematically it makes sense as well. If you look at this equation here, if we want to increase the bond order, we need to either increase the number of bonding electrons, or we need to decrease the number of anti-bonding electrons. And both of those will then result in an increase in bond order. So to write that out, if we add electrons to a bonding orbital, the bond order is going to go up. And then if we add electrons to anti-bonding orbitals, it will go down. And the opposite is true if we take electrons away. So if we remove electrons from a bonding orbital, the bond order will go down. If we remove electrons from an anti-bonding orbital, the bond order will go up. So these two statements and their opposites are all true. And so if we're looking to increase the bond order, we can add electrons to a bonding orbital. This is going to decrease the bond order. Choice C is removing electrons from a bonding orbital. That will also decrease bond order. And then choice D, removing electrons from an anti-bonding orbital, is the other way to increase the bond order. So choice E is 2 of these. Those 2, A and D, will both lead to an increase in the bond order. Okay? Any questions on this? Or am I, yeah? Yeah, so the correct answer would still be 2 of these, but it would be B and C instead of A and D. That's correct. So decreasing the bond order, you just have to do the opposite. You have to either remove electrons from bonding orbitals or add electrons to anti-bonding orbitals. Any other questions? All right, so then the next one, which is the last question on this review from chapter 4, is going to deal with using molecular orbital theory to predict some chemical property. And usually the two properties we're interested in are bond order, which again relates to the number of shared electron pairs and how strong the bond is, or number of unpaired electrons. So these are two things we could ask you. I'm asking you both of them here just to get you used to how we do that. So when we're doing molecular orbital theory, what we really need to be able to remember for these types of problems is the order that the molecular orbitals come in these different types of molecules. So as I said, we're only dealing with diatomic molecules. And so we have, in this case, it's O2 plus. And so we have to remember that the correct order for oxygen, fluorine, neon, the second half of the P block in the periodic table, is going to have the first orbital, the lowest energy orbital, is going to be a sigma orbital 2s. So the 2s orbitals on each oxygen mix together to give sigma and sigma star, where again, sigma is the bonding, sigma star is anti-bonding. Those are always the first two. And then when the p orbitals mix together, remember there's two types of bonds that can form from p orbitals. There's sigma bonds, where the two go head to head, and there's pi bonds, where the two orbitals align side to side. And so when we mix the 2p orbitals in oxygen, the first orbital level that derives from 2p is also a sigma. And then you have the pi, so the two bonding orbitals are the first two that come within the 2p set. And then it's going to be pi star, and then it's going to be sigma star. And these all derive from the 2p orbitals. All right, and remember, each pi level has two degenerate orbitals, both orbitals at the same energy level that we'd have to populate. So this is the order of the orbitals for oxygen, lowest to highest. That's really what you have to remember to be able to answer questions like this. As we showed in class, you can also show on the diagram where the atomic orbitals that these came from. This part is not terribly important for answering these types of questions, but it does give more completeness to the diagram. So as we sort of already said, when you mix two s orbitals together, you get sigma and sigma star. And then these orbital levels up here come from mixing two sets of 2p orbitals. So each oxygen has three 2p orbitals. So when you mix them together, you're going to get 6 molecular orbitals, and that's these 6 here in the middle of the diagram, or the top part of the diagram. And you draw dashed lines to show which atomic orbitals contribute to each molecular orbital. So that's a more complete diagram, but as I said, all we really need here is the center part and having those in the correct order to be able to populate them with electrons. So once we have the correct ordering of the orbitals, we need to figure out how many electrons to put into them. So we're talking about here O2 plus, which is called dioxygenyl cation. And so we have to count the electrons, and we just count valence electrons like we would for when we're doing the Lewis structure, no difference there. And so in this case, it's going to be 2 oxygens. If we go back to the periodic table and find where oxygen is also in group 6, so it's going to give us 6 valence electrons for each oxygen. Okay? So 6 valence electrons, it's a positive charge, so we have to subtract one of those, and that's going to give us a total of 11 valence electrons. And the one thing that molecular orbital theory does that's vastly superior to valence bond theory is it very easily allows us to make predictions about species that have odd numbers of electrons. Valence bond theory, where you pair all the electrons, works pretty well in most cases when you have even numbers of electrons. But in a situation like this, when you have an odd number of electrons, valence bond theory would be not give you any realistic information. So now we have 11 electrons. We're going to put them into this diagram here. And again, we follow the rules for filling orbitals that we already learned for atomic orbitals, which is we fill the lowest orbitals first, then to the highest, and we have to make sure we follow Hund's rule to pair the electrons correctly as well. So we're going to go 1, 2, 3, 4, 5, 6. When we get to this level, we go 7, 8, 9, 10, and then the last electron has to go up here. So just like atomic orbitals, each molecular orbital can only have 2 electrons in them, and if there are 2 electrons, one has to be up, one has to be down. And so this is the configuration that we get. If we want to write out the configuration for this, we would get sigma 2s2, so we have 2 electrons there, sigma star 2s2, sigma 2p2, pi 2p4, and then pi star 2p1. So those 11 electrons get apportioned in this way. This is another way we could potentially have answer choices in questions like this. If we ask you for the correct electron configuration of O2 plus, this is what you would select. But what this problem is asking for is the bond order and the number of unpaired electrons. And so for the bond order, remember it's that equation where we do 1/2 times the number of bonding electrons minus antibonding. So we find the electrons that are in bonding orbitals, which are the ones that are labeled without stars. So we have 2 electrons in this bonding orbital, we have 2 more up here, 2, and then 2. So 2, 4, 6, 8 of our 11 electrons are in bonding orbitals. If there's 8 electrons in bonding orbitals, there better be 3 in antibonding orbitals because there's only 11 total. And we see that these 2 electrons in the sigma star 2s and this 1 electron up here in pi star, all 3 of those are in antibonding orbitals. They're in orbitals that are labeled with asterisks or stars. So it's 8 minus 3, what we put into that equation. And that gives us a bond order of 2.5. So even though the simpler bonding theories like valence bond theory don't allow you to predict half bond orders, in molecular orbital theory, it's going to happen anytime you have an odd number of electrons. So it's going to be a bond order of 2.5, which means the bond order is in between 2 and 3, somewhere in between a double and a triple, in terms of how strong you would expect that bond to be. And then the number of unpaired electrons, we just have to look at the diagram that we drew. And we only need to consider the partially filled orbitals. So there's 1 lone electron up here that's going to be unpaired. That one there doesn't have any other electron that's spin down with it, so it's going to be just 1 unpaired electron. Okay? So any questions on this? Over here? So if you have a heterodiatomic, which means 2 different elements, we will specify what order you should draw the orbitals in. So there are 2 different ways of drawing the molecular orbitals for diatomic molecules. There's this one that I showed here, but then what we should be aware of is in nitrogen, carbon, and boron, the first 3 elements in the p block, these 2 orbitals, the sigma 2p and the pi 2p, flip their order. If it's a diatomic that has 2 different elements in it, like NO, we would specify what order that comes in if it matters for the question we're asking. If it doesn't matter, then you do it either way. So it's not easy to predict what order the orbitals come in, but you would still just write these orbitals out in whatever order is appropriate and then fill them with the correct number of electrons, which for that one would also be 11. So for NO, you get a very similar diagram to this, although I don't remember off the top of my head which of these orbital levels comes first, but they're both filled anyway, so it doesn't really matter for things like bond order especially. Yeah, so heterodiatomics work the same way, you just have to know what order they come in, which will tell you if it's important. Any other questions? All right, so that takes us to the end of chapter 4. As you can see, there's about 5 questions on this chapter, so it's going to be a little bit more heavy on chapters 5 and 6, which are all the stoichiometry and chemical equations stuff that we've been doing more recently. So let's move on then to that. So the first topic we dealt with was atomic mass, which is the idea that we learned at the very beginning of the course that each isotope has a mass number associated with it, which is determined by the number of protons and electrons. And then in a natural sample of an element, you're going to have a mixture of isotopes, and the reported atomic mass for that element, which you get from the periodic table, is actually the weighted average of all the isotopes. So that's what we're asked to do here. We have a hypothetical element with an atomic mass of 132.2145, and we're telling you that it has 2 stable isotopes, a 131 and a 134 isotope, with the respective masses given. The reason that those masses are not exactly 131 and 134 is because of Einstein's E equals mc squared, but we give you the mass of the isotope specifically here. We want to know what is the percent abundance of this isotope 134, and we want to answer with 2 decimal places. So there's only really one equation that's associated with the concept of atomic mass here, which is that the atomic mass of an element is equal to the fractional abundance of one isotope, which we'll call A, times its mass. So when we say weighted average, it's not just a simple average of the masses, it's where we have to multiply each mass by the abundance of that isotope before adding them together. And then it's going to be the abundance of the second isotope times its mass, and you keep going on for however many isotopes you have. Alright, so however many isotopes you have, you just multiply their abundance by their mass and add them together to get the atomic mass. The abundance is the percent divided by 100. It's the fraction of that element or that isotope that exists in that element. So this is the equation we deal with, and when we're doing problems like this, we just have to figure out what's given to us and what our unknown is. So here we're given There's only 2 isotopes in this case. We don't have to worry about any more than that. We're given the atomic mass, which is this number here. The abundance of the first isotope we don't know. That's going to be an unknown. We're given the mass of each isotope. And we have another abundance of whatever our second isotope, which we don't know. All right, so this is a common situation. We don't know either of the abundances or the percentages for these isotopes. That's what we have to find here. And because we have 2 unknowns in this problem, we have to come up with a second equation that relates the 2, which is always going to be that the sum of the abundances, the fractional abundances, equals 1. In this case, only 2. If it was more than 2, the sum of all of those would equal 1. And so then we can start putting numbers in that are related now to this problem. So the first equation, which is the atomic mass equation, we're given that the atomic mass is 132.2145. That's equal to the abundance of the first isotope, which I'll call X, multiplied by its mass, which is 130.9856. Plus the abundance of the second isotope, which we're calling Y, times its mass, which is also given here, 133.9767. From this second equation here, what we're solving for is the abundance of 134. So we're solving here for Y. That's what we want to solve for. So Y is equal to 1 minus X. Actually, no, we want to do it the other way. We want to get rid of X from the equation. So X is equal to 1 minus Y. If you solve for the wrong one, you just have to make sure you keep straight what you're looking at. So we're going to put that back into there. And so we rewrite this equation as 132.2145, which is the atomic mass, is equal to the abundance of the first element, which is given as 1 minus the abundance of the second, 1 minus Y, times its mass. And then Y times 133.9767. And then you plug this into the magical algebra machine, which unfortunately you won't have available on the test. And so Y is the abundance of the 134 isotope, which is what we're looking for, which is 0.4109 when I did the algebra. But then keep in mind we can ask you for either fractional abundance or percent abundance, and percent is always the fraction times 100. So if we want to find the percent, it's going to be that number, 0.4109 times 100, which comes out to 41.09%. All right. So in these types of problems that deal with atomic masses and isotope abundances, this equation that I wrote up here is the only equation you have to worry about. But keep in mind that there could be different unknowns depending on what we're asking you to find for. And if you have both abundances, or if those are both unknown, then you have to use the second equation and do a little bit of substitution. Okay, any questions on that? All right, so that's the definition of atomic mass. The more important thing for a lot of these problems is how do we use it. All right, so going on to the next question here, we want to know how many moles of sodium ions are present in 65.65 grams of sodium phosphate. So this is a conversion involving moles. There's a lot of different types of these that you'll potentially have to deal with on the exam, and it's very important for a lot of the other types of problems we'll do. So here we're just converting a mass into a number of moles, and so we should automatically think of atomic mass. But the first thing we need to be able to do is get the correct chemical formula for this, because we don't know what that is right now. We need that to find the molar mass. And so if we have sodium phosphate, sodium on the periodic table is over here in the first column, atomic number 11. It's group 1A. So we know that when sodium forms ionic compounds, it's going to make +1 cation. So the cation in this compound is sodium plus. And then we have to remember our polyatomics from chapter 3. Phosphate is PO4 3-. And then we just cross the charges to make them into subscripts to get the correct formula, which is Na3PO4. So the correct chemical formula for sodium phosphate is Na3PO4. Since we're converting a mass into a number of moles, we should recognize that we need the molar mass of this compound as well. And so the molar mass, which is often abbreviated as MW for molar weight or molecular weight, is just going to be 3 times the atomic mass of sodium. So we sum that, and so we go back to the periodic table. Sodium is number 11 with the atomic mass below the element 22.99. Sodium phosphate has 1 phosphorus, and we need its atomic mass. It's going to drive me into my grave if this room doesn't have a periodic table and I have to keep flipping back and forth. But yeah, but then people on the other side of the room complain, so I can't see the screen now, so there's no good solution, except for putting a periodic table maybe on that wall, but that's above my pay grade. All right, so then phosphorus is here, it's 30.97 is the atomic mass of phosphorus, so we include that. And then oxygen, we have 4 of them, and those are 16. I'm not going to flip back yet again to the periodic table. So those are atomic mass of 16. So we need the molecular mass, which is the molar mass, which is the sum of all the atomic masses. And so what we get for this one is 163.94 grams per mole. So that means 1 mole of this compound has a mass of 163.94 grams. And now we have all the information we need to do the conversion. So what we're looking for, and again, whenever you're doing conversion problems like this or other stoichiometry problems that we'll get to here a little bit later, you want to look at what the question is asking for. So we're looking for moles of sodium ions, which is Na+, and we don't want to stop doing conversions until we've converted our units correctly into that. So it's important to write your units out, and it's important to think about what it is that the problem is asking you for. So our starting amount is 65.65 grams of sodium phosphate. And then we can use the molar mass here that we just found to convert mass into moles. So 1 mole of sodium phosphate has a mass of 163.94 grams. And this is the part where a lot of you would stop and then you would get the question wrong because of that, because we're not looking for moles of sodium phosphate, we're looking for moles of sodium ions, Na+, and we know from the chemical formula Na3PO4 that there's 3 moles of Na+ for every 1 mole of sodium phosphate. So that's what these subscripts and chemical formulas tell us. In addition to explaining things at the atomic level, they also relate to the number of moles of each element in the substance. And so we have to remember to do this last conversion here to be able to get the answer correct. And that's why writing out quantities in units is very helpful, so you know then when it's okay to stop. So once we've gotten to moles of sodium plus, we just run the numbers and we get 1.201. And since it's a Blackboard question, you would just want to enter in the number. So try your best to always follow the directions in Blackboard so I don't have to go back and regrade things. It's much appreciated. Okay, questions on this one? Yeah?
So the very first part that you did, was just find the molecular formula.
Yes, and we didn't give it to you. You have to translate the name into the formula. And since it's an ionic compound, we just balance the charges to figure out how many of each ion there are. That's correct. Yeah? That's the given mass of sodium phosphate. That's what we're starting with, the quantity we're starting with. We're trying to figure out the moles of sodium plus in that much sodium phosphate. All right, anything else? All right, moving on to the next one. The next type of problem that is very common on this exam deals with converting mass percents into chemical formulas, or in a related sense using combustion analysis to do the same thing. And so what we have here is a compound called catechol, which has a mass percent of 65.4 for carbon, 5.49 for hydrogen, and 29.1 for oxygen. We want to know what is the empirical formula. So the empirical formula is going to be the elements in their lowest whole number ratios, and they have to be whole numbers. So right away we can eliminate choice D because an empirical formula will never have a fractional subscript in it. We could also, if we wanted to, eliminate choice C because that's not an empirical formula at all, because we could reduce that down to C3H3O. So even before we start the problem, we could eliminate 2 answer choices. So sometimes a little bit of strategy like this is helpful, especially if you're in a hurry to finish a question on the exam and you want to make it a little bit easier for yourself, try to find answers that are just completely unreasonable and get rid of them. And give yourselves, even if you have to guess a little bit, give yourselves at least a better chance of guessing right. So we're down to 3 answer choices, but we can't distinguish those 3 very easily. So let's go through and do the problem. So whenever we have a mass percent problem where we're converting mass percent into a chemical formula, we have to assume an amount of the substance, and the convenient way to do this is to assume 100 grams. Because when you have 100 grams of this substance, now we know that the mass of each of the elements is going to be 65.4, 5.49, and 29.1. So if we have 100 grams of compound, we can then find the moles of each element that are in that compound. So the moles of carbon, we're going to have 65.4 grams of carbon. That's the mass percent of carbon, which in 100 grams would mean there's that much carbon. And we just convert to moles using the atomic mass. In this case, for carbon, it's 12.01. So this substance is going to have 5.45 moles of carbon. We do the same thing for hydrogen. The percent for hydrogen is 5.49, so this 100 gram sample has 5.49 grams of hydrogen. The atomic mass for hydrogen is just over 1.008. So these are all from the periodic table. I don't want to spend time flipping back and forth again. And so we have a similar amount of hydrogen, almost identical amount, 5.44 moles. And then finally what we have is, for oxygen, 29.1 grams. And the atomic mass of oxygen is 16. So that comes out to 1.82 moles. Alright, so with these 3 numbers then we can find an empirical formula which is the lowest whole number ratio. So we write those out, but remember we can't have fractional subscripts, so we have to reduce them. So if we have 5.45 moles of carbon, 5.44 moles of hydrogen, and 1.82 moles of oxygen, we divide all 3 of these by the smallest of those numbers to reduce them to simple fractions or whole numbers. And this works out right away without having to do any additional work, C3H3O. Alright. So that's the ratio of carbon to hydrogen to oxygen. It's 3 to 3 to 1, and we get a correct answer then would be A. Now the one mistake that a lot of people make in these problems, which didn't come up in this specific one but could come up on some of the exam problems, if you do this step here where you divide the 3 or however many elements you have to get the ratios, it doesn't always come out to a whole number. So if it comes out to a fraction or a decimal, unless it's really close to a whole number, like for example this one here would have probably been, one of these would have been a little bit more than 3, like 3.001 or something, but that's close enough. But if you get a number that's pretty far away from a whole number, like 3.33 or 1.25 or 1.5, you want to then take that equation and multiply it by a small whole number to get rid of the fractions. You don't want to just do a bunch of rounding in these problems. So if your number that you get has a 0.25 or a 0.75 in it, you multiply by 4, the whole thing, the whole formula by 4. 0.33 or 0.67, you multiply it by 3. 0.5, you multiply by 2, and so on. So sometimes when you do this, you won't get whole numbers right away. You might get something like this, choice D, and then you'd have to multiply the formula by 3 to get it into a correct empirical formula that only has whole numbers in it. So that's the mistake that a lot of people make, is doing too much rounding on these, which you really don't want to. You want to avoid that pitfall. Okay. Yep. Yes, but you would have to ask for. You have more information to find that. So, in order to find the molecular formula, you would have had to also know something about the molar mass, which we didn't give you here. But yes, choice C could be the molecular formula, and I think in fact it is for catechol, but we don't have enough information in this problem to determine that. But choice C is definitely not the empirical formula because it's not the smallest whole number ratio. Yep. No, so once you have the ratios, whatever you do to one, you have to do to others. So let's say we got this answer, CHO 0.333. If we got this as our answer, we'd have to take everything and multiply it by 3. That would then give us the same answer that we got, which is C3H3O. So to get rid of that fraction, you multiply this by 3, but you have to do the same thing to all of them to keep the ratio the same. Anything else? All right, on to the next one. Here we're balancing an equation. We want to know what's the sum of the coefficients when this equation is balanced with smallest whole numbers. So if we don't specify on the exam that you should use the smallest whole number coefficients, please do that. Anytime we ask you to balance an equation, make sure that it's with the smallest possible coefficients, no fractions, and that if you can reduce it down, you do that. Okay, so this one it does specify, but it won't always say that. So we have this type of equation here, which is a combustion reaction. So we just have to figure out okay, so those are the reactants and products, and we just have to make sure that the elements are balanced on each side. So the way that I like to do this again is I set one of the coefficients to 1, whatever I think the most complicated species, one that has the most elements in it, set it to 1. And then when we're balancing elements, look for ones that appear only once on both sides of the equation. So if we look at oxygen, we see that we have oxygen here, we have oxygen here, we have oxygen in both of our products. So that's not a good one to start with because there's a huge number of possible combinations of coefficients that will result in oxygen being balanced, but we don't know what that is right away. So we're going to start balancing carbon and hydrogen first because carbon only appears in this reactant and only appears in CO2 as the product, and hydrogen only appears here and on the reaction side and in H2O as the product. So we can balance those two first. So if we have 12 carbons from our reactant, we need to have 12 CO2s to balance that. If we have 10 hydrogens, we need to have 5 waters to balance that. And so then those are the two coefficients we get for CO2 and water. And then the last thing to do is make sure oxygen is balanced by adding a coefficient to O2. So on the left side of the equation, we have 12 times 2 is 24 plus 5. We have 29 oxygens on the right side of the equation. 12 times 2 plus 5 is 29. On the left side of the equation, this only has 1 oxygen, and so we need 28 more. And so the way we can get 28 oxygens from O2 is to put a 14 in front of it. All right? So that's the coefficient that goes in front of oxygen, and now everything should check out and be balanced. And all this is asking for then is the sum of the coefficients. We wouldn't normally include the 1 here, but there's a coefficient of 1 whenever 1 is not listed. We have 14, we have 12 and 5 on the product side. Those are the smallest numbers. We can't reduce those down at all. And so the sum becomes 32. All right, so very commonly we'll ask you to balance a chemical equation, and then we'll want you to provide 1 or more of the coefficients, or a sum of those. Just read the questions carefully to see what we're asking for. Question over here? So this one you could have used the oxidation number approach, I suppose. It would have been a little bit more complicated. If it's a redox reaction, you can do it. It's just that this one is pretty complicated with 12 carbons and 10 hydrogens. Now the not very instructive answer on when to know how to use oxidation numbers is use oxidation numbers for number 19 and 20 on the test, but don't use them for the other ones because those are the ones that are specifically about redox reactions. But if it is a redox reaction, which this technically is, you could potentially use that. It's more complicated when your species have 12 carbons and 14 oxygen, or that are changing all their oxidation states. It becomes a little more difficult that way, but it could work. It should work anyway. But yeah, I think for combustion reactions where all the species are neutral and it's not an aqueous reaction, just use the sort of method by inspection is the best way to go for those. All right, any other questions? All right, on to the next one, which is getting into stoichiometry now. So here's another combustion reaction. C4H10 in this case, we want to burn it in the presence of O2, and we want to find the mass of carbon dioxide that forms if we're burning 3.25 grams of the butane. So this is another problem that requires us to first balance the chemical equation, which isn't given here. Now we should recognize by now that combustion reactions are very common, and they have a very similar format for all of them. So we have whatever substance we're burning is one of the reactants. The other reactant is O2. And then the products of a combustion reaction, which we talked about in the context of also combustion analysis, are always carbon dioxide and water. So all of the carbon goes into carbon dioxide, all of the hydrogen from your reactants goes into water, and then oxygen comes either from the reactant or the O2 that's present, or both. All right, so that's the reactants and products for a combustion reaction. Now that being said, in this problem here we have a mass of C4H10, and we're trying to convert that into a mass of CO2. So as long as we know the correct ratio of those two substances, even if we didn't write the full balanced chemical equation, we'd be okay. We just need to know the ratio of butane to carbon dioxide to be able to answer this without even having the other reactants and products present necessarily. But if we want to write the full equation, this is what it looks like. So we're going to have a 4 in front of CO2, a 5 in front of water, and in this case it's going to be 13 oxygen, so it's going to be 13 halves in front of O2. If fractional coefficients bother you, then you would want to take every coefficient and double it. So just like we talked about for empirical formulas, if you double one coefficient, you have to double all of them. And so the correct form of this equation, fully balanced with whole number coefficients, would be this. We double every coefficient in the original form and get an equation that looks like this. All right, so the form of the balanced equation you write is not terribly important. We can answer this question using either form of this balanced equation, or as I said, even if you don't have the full balanced equation, just knowing that all of the carbon goes into CO2 tells you that you have a 1 to 4 mole ratio of the two by balancing the carbon atoms. So there's a lot of different ways to get this information that we need, but this is what our starting point is going to have to always be a balanced equation, or at least enough of a balanced equation to know the mole ratios of the substances that we're considering. And now we're ready to go ahead and solve the problem. So we're looking for the mass of CO2 that forms, starting with 3.25 grams of butane, which is C4H10. And here I was nice and I gave you at least the molar mass of that one. So when we're starting a stoichiometry problem, the first thing we should look to do is convert into moles. If we're given mass of a reactant or product, we use molar mass to convert into moles, as we've already seen in a separate context today. So 1 mole of C4H10 has a mass of 58.14 grams. And then once you have moles of one substance, you can convert into moles of the other substance using the balanced chemical equation. So whichever form of this equation you use, if we use the bottom one with all whole numbers, we find that there's a coefficient of 8 in front of CO2. So that means we're going to form 8 moles of CO2 for every 2 moles of C4H10 that reacts. Or alternatively, we could C4H10. We could write that as 4 to 1 if we prefer that way. It'll give us the same number, obviously. And so moles of C4H10 cancels. That converts into moles of CO2. But we're looking for a mass in grams. So the last step then is to again use molar masses. I should have given it to you here for CO2 so you don't have to calculate it. But CO2 is 12 plus 32, which is 44. So 44.01 grams of CO2 for every 1 mole of CO2. And that gives us then finally the mass of product, which comes out to 9.84. All right, so this was a straightforward mass-to-mass stoichiometry problem. We're giving you a mass of one of the reactants and asking you to find the mass of the product that can form when that reactant is consumed. So questions on this topic? All right, so then taking a step further, we have problem 11 here, which is another stoichiometry problem, but here we're looking for a theoretical yield where we have we give you the chemical equation in this case, so that's already taken care of for us, but we're taking 29.6 grams of gold, we're combining it with 50 milliliters of 4 molar hypochloric acid, HOCl, which has a molar mass of 54.46, and we're doing that in the presence of excess HCl. So we want to know what's the mass of gold chloride, AuCl3, that can form in this reaction. So what we have to recognize here is that in this problem we're given the amounts of 2 reactants. Okay, so we're telling you that we have 29.6 grams of gold, and we're also telling you that we have 50 milliliters of this HOCl solution. So whenever we have amounts for 2 or more reactants, we have to determine which of those is a limiting reactant, and there's no way around that. So here we're told that we have 29.6 grams of gold. We're told that HCl is in excess, so we don't have to worry about the amount of that. But then for HOCl, we see that we have 50 milliliters and this is a 4 molar solution, so we have the amount of that as well. So if we're going to find out how much of this product forms, we have to find out which of our reactants is the limiting reactant, which will then determine the maximum amount of product that we can get. And so this problem here combines concepts from chapters 5 and 6, where we're starting with a mass of one reactant and then a molarity and a volume for the second reactant. We have to figure out which of those is a limiting reactant and how do they react with each other. So when we want to find a limiting reactant, there's a few ways we can do this, and the way that I taught in class is to find what's called a stoichiometric ratio. And so that first involves finding the moles of each reactant. So we're going to find the moles of gold. This is a mass amount, so we just use atomic mass to go from grams into moles. So because it's an element, we can find its atomic mass on the periodic table. Au is way down here, atomic number 79, with a mass of 196.97. Okay, so that's the molar mass or atomic mass of gold. So it's going to be 1 mole has a mass of 196.97 grams. And so that gives us 0.150 moles of gold. But then that alone doesn't tell us if it's the limiting reactant. We have to find what I call the stoichiometric ratio, which is taking that number, 0.150, and then dividing it by the coefficient in the balanced chemical equation, which is a 2 for Au. So we have to take the number and divide it by the coefficient, and that's going to be 0.075. And then we're going to do the same thing for the other reactant. We're going to find the moles of that reactant divided by the coefficient, and we're going to compare these two numbers here that I abbreviate as R. So then for HOCl, which is the other reactant that we have information about how much of it is present, in this case we're going to use volume and molarity to find the number of moles. So we have 50 milliliters of our solution, so that's the amount of solution that we have. And remember then that this 4.00 molar, capital M, tells us that we have 4 moles per liter. And then that would also be equivalent to saying 4 moles per 1,000 milliliters. That's a little shortcut that I like to use. So this is another way of writing molarity, moles per liter or moles per 1,000 milliliters. And that then gives us moles directly just by multiplying those two and dividing by 1,000. So this comes out to 0.2. And then the stoichiometric ratio R is going to be that number divided by its coefficient, which is a 3, which comes out to 0.067. Alright, so if we compare the two numbers, 0.067, 0.075, the two stoichiometric ratios. The one that's smaller is identified as limiting reactant. So that substance there is limiting reactant. And remember, once we find what the limiting reactant is, we don't want to use these numbers anymore. We want to go back to the number of moles of that we had. And so we're going to use that to find finally the mass of product that forms. So once we know what the limiting reactant is, any other calculation we do, whether it's determining the amount of product that forms or determining the amount of the other reactant that is reacted with it, or anything about the chemical equation, we start with the moles of limiting reactant, which in this case is 0.2. So 0.20 moles of HOCl, that's the number of moles of limiting reactant. We want to find the amount of this product AuCl3, so we use mole ratios from the coefficients. So AuCl3 has a coefficient of 2 in front of it, and then that reactant has a coefficient of 3, so we multiply by 2 over 3 to convert into moles of gold chloride. And then we have to use the molar mass of gold 3 chloride, which is given to us here, 303.32, to convert moles back into grams. So these last few steps here are just like the problem we did before, converting moles of one substance into moles of another, and then moles back into grams. And it's asking for an answer with 2 decimal places and no units. So what I got was 40.4 something, and I forgot to write out the second decimal place. Anybody have it? 44. Okay. Now, if you got the last decimal place wrong, usually that's not a big deal because the we usually give you about a 1 or 2% window. So as long as you have the first decimal place right, you'll be fine. But anyway, follow the instructions on Blackboard, and this one would be 40.44 grams of gold 3 chloride as our product. Okay, so whenever you're given amounts of 2 or more reactants, you have to first determine the limiting reactant. The other way to do these problems, which if you're more comfortable with, go ahead and do it. There's nothing wrong with that way, is just do the problem twice. Start with each reactant and calculate the amount of product that forms from that, and then whatever those small numbers is smaller is going to be the correct answer, and whatever reactant you use to get that number would be the limiting reactant. So there is more than one way to do this. I like to quickly identify the limiting reactant because especially for more complicated problems that may ask you to, find something else or do a percent yield or whatever, it's just nice and comforting to know what the limiting reactant is and just get on your way. But if you want to just do the problem twice, you can also do it that way and just pick the smaller of the two numbers when you're determining how much of the product forms in these types of reactions. Question back here? Yes. Yeah, this script M is molar mass here. This is the molar mass of HOCl, and we don't need that one for this one. So if you have molarity and volume, you don't use the molar mass to find number of moles. You just use the molarity and the volume. Okay. Any other questions? Yeah. Yeah, I mean you have to find the limiting reactant. There's no way around that. But as I said, the way that I did it here was to identify the limiting reactant and then do the calculation. The other way to do it is just to do the calculation twice, starting with gold, 29.6 grams, or starting with HOCl, 50 milliliters, 4 molar, and then you can just do the problem twice and pick the smaller answer. But yeah, before you, at some level, you have to identify limiting reactant to get the correct answer. You can't just randomly pick one of the two and do it. You have to know which one's correct. Other questions? All right, on to number 12. So this one deals with the properties of aqueous solution. So we don't have a lot of concepts in this part of the course. There's mostly numerical stuff. But the one concept we did talk about was the idea that when substances dissolve in water, if they're certain types of substances, they dissociate into ions, and then if you have those ions present in solution, they conduct electricity. That's what we call an electrolyte solution. Whereas other types of substances, they don't dissociate, and they would not then conduct electricity. So if we're looking here, we're looking for a solution that would not conduct electricity at all. So we're looking for a non-electrolyte solution, as we would call it. And so what we just have to think about for these types of problems dealing with electrolytes is the different types of substances that we can dissolve in water and the different possibilities. So a strong electrolyte, which is one that conducts electricity really well, which is actually what we're not looking for here, but a strong electrolyte would be two different types of compounds that would dissolve in water to give a strong electrolyte. Either a soluble ionic compound, so if we dissolve any ionic compound in water, it dissociates into its individual ions and conducts electricity. And then the other type of compound that behaves very similarly, although it's technically a covalent compound, would be a strong acid. So both of these types of compounds, soluble ionic compounds and strong acids, when they dissolve in water, they give strong electrolyte solutions. Then the other one that would also still conduct electricity, but not as well, is a weak electrolyte solution. And the types of compounds that would be classified as weak electrolytes are weak acids or weak bases. All right, so both of these would conduct electricity. It's just that strong electrolytes conduct electricity better. So those are the two categories of compounds that dissociate when you dissolve them. Weak electrolytes don't dissociate very much, but they still produce some ions and still conduct electricity to some extent. And then the ones that are non-electrolytes, the ones that don't conduct electricity at all, those would be covalent compounds that are not acids or bases. And these ones do not conduct any electricity at all. So if we're looking for in this question, the type of compound that would, the type of solution that would not conduct electricity at all, what we're looking for is a covalent compound that's not an acid or a base. All right, so the first answer choice, HNO3, we should recognize that that's one of our strong acids, nitric acid. And remember that acid formulas tend to start with hydrogen as well, so that can kind of clue you in, but not always the case. Calcium chloride is an ionic compound and it's soluble, so it would also be a strong electrolyte. Now this one here, H2CO, it kind of looks like it might be an acid, but do we have a CO2- anion in our list of polyatomic anions? No. So in this case, the hydrogen is bonded to carbon. And in general, compounds that have hydrogen bonded to carbon are not acids at all. Okay, so this one would be a covalent compound, but it's not an acid or a base. So this one would be our non-electrolyte. So we think that that's our answer choice. Let's check the other two to make sure. KOH is a strong base, but it's also classified as an ionic compound. So when it dissolves in water, it gives electrical conductivity. And then H3PO4 is not a strong acid, but it is an acid, and it's a weak one. And so this would at least conduct electricity a little bit when it's dissolved in water. So of these 5 answer choices, the only one that is completely non-electrolytic is going to be choice C, H2CO. So you have to be able to recognize which compounds are acids. You know, we have a few different categories of acids that we learned back in chapter 3, the binary acids as well as the oxo acids, ones that have polyatomic anions. And if it's a covalent compound that's not one of those acids, then you can conclude that it's going to be a non-electrolyte solution. Classic example of these would be things like CH3OH, methanol. So stuff like that where you don't have an acid, but you still have a covalent compound that can dissolve in water and would be a non-electrolyte. All right, questions on this topic? So the reason we know that's from our solubility rules, so which is another important topic in chapter 6. So from solubility rules, halide compounds that have, especially the chloride, bromide, and iodide compounds, those are almost always soluble unless they're paired with silver, lead, copper, and mercury. So there's a few exceptions for chlorides and bromides, but most of those are soluble. So this would be a soluble chloride compound. Other questions? Yeah? So yeah, covalent compounds are groups of non-metal atoms bonded together, and then ionic compounds will be a metal with a non-metal, either just one of each if it's a binary ionic compound, or a metal with a polyatomic anion. There's always going to have at least one metal in it. All right, other questions? Okay, let's go on to the next one then. So this question deals with molarity. We have a solution of calcium perchlorate. It has 25.65 grams of that dissolved in 1.23 liters of solution. What is the concentration of perchlorate ions? So again, this is another one we have to look closely at what the question is asking. And we know the concentration of perchlorate ions in units of molarity. All right, another numerical type question. So once again, we need the correct chemical formula to be able to do this. So a calcium compound, so calcium is in the second column of the periodic table if we find it there. So it's going to make a 2+ cation. And then we still have to remember all of our polyatomic anions. They're not going to go away anytime soon, or really anytime while you're still a chemistry student. So we have perchlorate, which is ClO4 with a 1- charge. So you have to be able to remember those. And so if we have a 2+ cation and a 1- anion, we need to have a 1:2 ratio to balance charge. So the correct formula for calcium perchlorate is Ca and then ClO4 taken twice. All right, so that's our chemical formula. I gave you the molar mass, but you need to also have the chemical formula to answer this question because we're looking for the concentration of perchlorate ions. And so if we're looking for that molarity of ClO4-, the two quantities that we need are the moles of perchlorate, and we also need then the volume of solution in liters. All right, so this number here is given to us. The volume is 1.23 liters as we're told. But we need to do some conversions to find moles of perchlorate because we're just given a mass of the solute that we dissolved in there to make that solution. So this again is just a bunch of mole conversions that should be become very routine for us and where we do them. So moles of perchlorate, we have 25.65 grams of calcium perchlorate. And then we're going to use the molar mass that we're given to convert grams into moles. That's going to again give us the moles of the whole ionic compound, calcium perchlorate. So 238.98 is the molar mass that we're given. So that's moles of calcium perchlorate, but then again, reading the question closely and looking at what we need moles of perchlorate anions. Because when a compound dissolves in water, it breaks up into its ions. And so in this case, if we dissolve 1 mole of calcium perchlorate, what we see is that from the chemical formula, we have 2 moles of perchlorate anions. So 2 moles of ClO4 minus for every 1 mole of calcium perchlorate. Again, this last step here is the one that's most often forgotten when we're doing problems like this. So look closely at what substance we were asking about. In this case, it's the individual perchlorate anions. We have to do that last step here. And keeping 4 sig figs, we get 0.2147 moles of perchlorate. We plug that back into here in the numerator of this equation. And 0.2147 moles per liter gives us a molarity of 0.175 molar, and you would enter in just the number 0.175. Okay, so whenever you're finding molarity, you need moles and you need liters of solution, but in this case, we had to be a little bit careful and look at moles of what substance are we talking about. Questions? Yep. Yeah, right now molarity is really the only concentration unit we're dealing with. There are others. It might say, and here I say concentration in capital M, which tells you that it's molarity, but even if we don't specify, you would do it as molarity. Yes. All right, other questions? All right, let's keep trucking on. All right, so here we have a solution of 0.254 molar NaCl with a volume of 225 milliliters, and we're adding 125 milliliters of water to this. So whenever a problem is set up like this, we have a solution of some compound, and then we're adding water to it to change the concentration. You should immediately think dilution. We're not doing any chemistry here. We're not reacting the NaCl with anything. We're just adding water to change the concentration. So whenever you think of dilution, there's only one equation that really applies, which is M1V1 equals M2V2. So the molarity of the first solution times its volume equals the molarity of the second solution times its volume after you do the dilution. So what we're looking for here is the final molarity. We're looking for what is the final concentration of NaCl. So we're looking for M2, and so it's going to be M1V1 divided by V2. And then what we have to think of here is what information we already have. So the initial molarity is given to us. M1 here is 0.254. V1 is the initial volume, which is 225 milliliters. But now we have to find what the final volume is, V2, and this is the one that's not directly given to us. So remember, V2 is the final volume after we add the additional water. It's not just the amount of water we add. So V2 is going to be the amount that we start with, 225 milliliters, plus the amount of water that we add, 125. We're told here to assume that the volumes are additive, which is, in most cases, a good assumption. So V2 is the amount that we started with, plus the amount of water we add, or the final volume then would be 350 milliliters. So whenever you're doing dilution problems, keep in mind that the volumes we're talking about are the total volumes of the solution. They're not volumes of water that we've added or anything like that. Okay, so that's the V2 that we need, so we just have to plug the numbers in to get our answer. So we have 0.254 molar, and in problems like this, it doesn't matter what volume unit we use because they're going to cancel out. So our V1 is 225 milliliters, and then our V2, as we just found, is 350 milliliters. So we don't have to convert those into liters because the units will cancel out when they're written like this as a ratio. So numerically then what it comes out to is 0.163 molar. All right, we diluted the solution and the molarity got smaller, the volume got larger. All right, questions on dilution? All right, we'll just keep going then, because it's got about 6 more to do. All right, here we're looking for which of the following mixtures will not form a precipitate. So we're mixing together, in most cases, two ionic compounds, and we're trying to find which one will not form a precipitate. So the way we want to approach these problems about identifying precipitates in ionic reactions is, remember, we take the cation and the anion from the two pairs and we swap them with each other. So the cation from the first compound gets paired with the anion from the second, and the anion from the first compound gets paired with the cation from the second. We have to identify which of those combinations, if any, are going to be insoluble by using the solubility rules. All right, so for choice A here, we have KCl plus silver nitrate. And so when potassium pairs with nitrate, we get KNO3. And then the second combination is silver pairing with chloride, which gives us AgCl. So we have to identify if either or both of these are insoluble. The ones that are obvious, potassium salts or any sodium, lithium, all those are going to be soluble. Anything with nitrate is also soluble. So this one won't precipitate, but silver chloride is one of our insoluble chloride salts. Remember, chloride salts of silver, mercury, lead, and copper one are all going to be insoluble. So this one forms a precipitate. So that's going to be, we're looking for the one that will not form. In choice B, what we have are ammonium sulfate and lead perchlorate. So the two products we get are ammonium paired with perchlorate, which is ammonium perchlorate. And then we get lead paired with sulfate, lead 2, so it's going to be PbSO4. And pretty much all lead 2 compounds are insoluble unless they have nitrate, perchlorate, or acetate with them. So because it's lead sulfate, this one's going to be insoluble. So when you're looking for insoluble compounds, look for silver and lead, because more often than not, those ones will be insoluble. So lead sulfate is insoluble, so that would form a precipitate. In choice C, we have sodium carbonate and barium chloride. So we're going to pair the sodium with the chloride, the sodium from the sodium carbonate with the chloride from the barium chloride. We get sodium chloride as one of our products. That's clearly soluble. We all know that salt is soluble in water. But then the second product is barium paired with carbonate. And carbonate is another one of those anions. It's like phosphate, where pretty much all of them are insoluble, except for the lithium, sodium, potassium, ammonium, all those ones. So this is another insoluble compound. And then for choice D, sodium pairs with chloride again, so we have NaCl again, and then iron pairing with hydroxide. So this is iron plus 3 because it's paired with 3 chlorides. So the correct formula would be FeOH3. But even if we didn't get that right, recognize that most hydroxide compounds are insoluble, especially with the transition metals. So this one's insoluble. And then finally, the last one, which I would hope is the correct answer, is when we pair calcium nitrate and ammonium chloride, we pair calcium with chloride to get CaCl2 is one of our products. And we saw earlier in one of the problems that this is a soluble chloride salt. Most chlorides are. And then the other product is going to be ammonium nitrate. And all ammonium compounds are soluble, all nitrate compounds are soluble. So both of these are soluble in this case. And so this would be the choice that gives us no precipitate. All right. So as I said in class, learning solubility rules can sometimes be a painful thing, but you want to look for the obvious ones first. Look for lithium, sodium, potassium, rubidium, all those group 1 cations, because those are always soluble. Look for the 3 anions, nitrate, perchlorate, and acetate, because those will always be soluble. And then also for insoluble compounds, look for, as I said, silver and lead. Those two are almost always insoluble. And by looking for the obvious ones in most of the problems, you can pick some things out and help yourself a lot just by looking at those. And then there's a few rules in there with especially like sulfate compounds and hydroxide compounds that are a little bit more difficult to learn, so spend some time familiarizing yourself with those. But most of the rules are pretty obvious and you don't have to think too hard about them. Okay, questions on solubility rules or precipitation? Yep. Yes, so if something is soluble, it will not form a precipitate, it will stay dissolved in solution. A precipitate is a solid that forms when 2 ions pair together that aren't soluble and they fall out from solution as a solid. Other questions? These would be, yeah, double replacement reactions is another way of saying that, yes. Anything else? Yeah. Usually. So for hydroxides, there's I don't know if usually is the right word, but they're insoluble except with the group 1A cations, ones that are always soluble, like lithium, sodium, and potassium, or NH4+, which is in that same category. So they're insoluble except when they're paired with that, and then the other exceptions are the heavier group 2 hydroxides. So that would be strontium, barium, and then I think calcium is the other one, yeah. So those 3 group 2 hydroxides are also soluble, but any other transition metal hydroxide or the lighter group 2 hydroxides, magnesium and beryllium, are all insoluble. So that's one of the ones that's a little bit annoying to learn, but I would say at least half the time it's insoluble, and especially if it's not with one of those special cations from group 1A or ammonium. Anything else? All right. On to the next one. All right, so this question has some similarities to the last one. We're mixing together 2 aqueous solutions, and we're asking for which are the spectator ions. So spectator ions are the ones that remain dissolved, the ones that are soluble on both sides of the chemical equation. And they're the ones that you would then cancel out if you're writing the net ionic equation. So for this problem here, we have to look at the balanced chemical equation. So we have barium nitrate. Barium is a +2 cation, so it's going to be barium with 2 nitrates. And then we're reacting that with sodium phosphate. We saw earlier that the correct formula for sodium phosphate is Na3PO4. And then we're getting 2 products from this. We're getting barium phosphate. So barium is +2, phosphate is +3. So the correct formula for that would be barium 3PO4 twice to balance the charges. And then the other product we're getting is sodium nitrate, NaNO3. Okay? So this is our precipitate. Phosphates are almost always insoluble unless they're paired with something like sodium. This one would remain dissolved. And now we have to put some coefficients in here. So we need a 3 here and a 2 there and a 6. And that's about as big as the coefficients we'll ever get for an ionic equation. Now you don't really need to have the coefficients drawn out correctly to identify spectator ions. I'm just doing this for completeness. What we want to look at in this case is which ions remain soluble on both sides of the equation. Now you might be able to identify it just from this equation here. We see that on both sides of the equation, sodium is part of an aqueous compound. Sodium phosphate is aqueous, sodium nitrate remains aqueous. So sodium would be one of our spectator ions. And we'll see the same thing for nitrate, aqueous compound, and really those are 2 of the obvious ones. When you, as I said, when you have compounds with sodium, they're always soluble, so sodium will almost always be a spectator ion, and same with nitrate. Compounds with nitrate are always soluble, so very often nitrate will be a spectator ion. So those are what we think it's going to be. If we want to go further and write this out in more detail, the way we do this is we write out the full ionic equation by separating out all of the dissolved aqueous compounds into their individual ions. So barium nitrate, 3 barium nitrates are going to separate into 3 barium 2+, and then we have a total of 6 nitrates, 3 times 2. Again, coefficient's not terribly important here, but we want to separate all these compounds into ions, and then the ions that appear on both sides would be identified as spectator ions. And then 2 phosphates on the reactant side. On the product side, we've said that barium phosphate is insoluble, so we don't separate that into ions. That stays as barium phosphate, solid. And then we still have 6 Na pluses from sodium nitrate, and then 6 NO3 minuses also from that compound. And then if we look at this form of the equation, what we see is that on both sides of the equation we have 6 Na pluses and we have 6 NO3 minuses on both sides. So sodium plus and NO3 minus by that are also our spectator ions. And so that gives us choice B as the correct answer. And then if we wanted to write a net ionic equation, which would be another question we could ask you, we take the spectator ions out. So the ones that appear on both sides, you can think of them as canceling out. And what we're left with then for our net ionic is 3 barium 2 plus 2 phosphates gives us barium phosphate. So the net ionic equation includes the ions that combine to form your precipitate. And you remove the two spectators, sodium plus and NO3 minus. So there's a few different ways of going about identifying spectator ions, but we just have to recognize that they are the ones that remain dissolved or as aqueous species on both sides of the chemical equation. So questions on that topic? All right, let's go on to the next one then. So in this one we have an acid-base problem. So we're taking a 2.34 gram sample of an unknown diprotic acid, which means it has 2 acidic protons, and we're neutralizing it with a 0.375 molar NaOH solution. It takes 40.9 milliliters of the solution to neutralize it, so we want to know what is the molar mass of the unknown acid. Okay? So because this is an unknown diprotic acid with 2 protons, I'll write the abbreviation as H2X. 2 acidic protons, just to keep that straight. And what we're looking for here is molar mass. And so when we're doing problems like this would be categorized as a titration problem. We're titrating an acid with a base or vice versa. And when we're doing these, we want to think about first what the question is asking us so we know what quantities we need. We don't want to just start, plugging numbers in and furiously trying to go after the problem without knowing what it's looking for. So this is looking for an unknown molar mass. And anytime we want to find an unknown molar mass, the 2 quantities we need are the mass of the unknown, which is H2X in this case, and we need the moles of the unknown. So the ratio of grams to moles gives us molar mass. We did a problem in class very similar to this just the other day, so hopefully this looks a little bit familiar. So we're looking for an unknown molar mass by finding the mass of the compound and dividing it by the number of moles. The mass of the compound is given to us. We see that we're using 2.34 grams of our unknown, so that quantity we already know. But we need to use the titration data to figure out what the moles of the unknown acid are and divide the two. So if we're going to do a titration, remember titration is just a fancy word of saying solution stoichiometry. There's nothing really different about it than that. We need to write out a balanced chemical equation, and we at least need to get the ratio of the 2 reactants correct, because that's what we're combining with each other, an acid and a base. All right, so we have H2X, which has 2 acidic protons, and so when we combine that with NaOH, which is our base, we need to have also 2 OH minuses present to neutralize that, so we have to put a coefficient of 2 in front of it. So that's the important part. The acid and the base in this case react in a 1:2 ratio because it's a diprotic acid with 2 protons. The products of this would be water. We get 2 moles of water because it's 2 H pluses and 2 OH minuses. And then we get our salt or ionic compound, which in this case would be Na2X. For titration problems, though, we don't really care about the products. We just need to make sure we have the ratio of the acid and base correct in our heads. And then from there, we can use the information in the problem to find how many moles of that acid we have, H2X. So we know that we used 40.9 milliliters of sodium hydroxide. We also know the concentration of that. So that's going to be our starting point, the molarity and volume of NaOH. We use the molarity once again to find moles of sodium hydroxide. So the molarity is 0.375 given to us in this problem, and that's moles per 1,000 milliliters or per 1 liter. I'm going to do it as 2 steps. So now we have moles of sodium hydroxide, and just like any other stoichiometry problem, once we have moles of one substance, we can find the moles of the other substance using the ratios, the coefficients. So there's going to be 1 mole of H2X present for every 2 moles of NaOH that we add in the titration, because it's a 1:2 ratio. And that gives us the number we need, which is 0.00767 moles. And so we put this number back up here to get the molar mass. and that comes out to 305.1 grams per mole. And that's the number you would enter. Okay, so with titrations, there's a lot of variability. This is only one example. We could ask you to find, the volume of the acid you have to add, or the volume of the base you have to add, or the molarity of the solution, or in this case, the molar mass. There's a lot of different things we can ask you for, but they all revolve around using molarity and volume and stoichiometry to convert moles of one substance into moles of another. Since that common theme is going to be there for really any type of stoichiometry problem. So questions on this one? All right, let's do the last two, which are no, sorry, three more, geez. It's a marathon, not a sprint. All right, here, the last three, though, are going to all deal with the concept of oxidation numbers. And so what we're looking for in this problem is the correct oxidation number for nitrogen. There's some rules that we follow for oxidation numbers, remember. We gave those in class recently. And here we're looking to pair these up with the correct one. All right, so the first one, HNO3. All right, so remember rules for oxidation numbers. Look for the obvious ones first. Hydrogen in any covalent compound is going to be +1. Oxygen in just about every covalent compound, unless it's bonded to itself or to fluorine, is going to be -2. And then the sum of the oxidation numbers has to equal the overall charge. So this is a neutral HNO3. So if we have a +1 and 3 -2s, what does nitrogen have to be to balance those? +5. So we've still got our wits about us. That's good. So we got +5 for nitrogen. And then for choice B, so that's incorrect because this one says +4. So that's not going to be our correct answer. We're looking for the one that's correct. In choice B, we have NO2. So again, covalent compound with oxygen, we should immediately think of oxygen as being -2 in almost every case. And if oxygen is -2, two -2s is -4. So that means nitrogen in this case would be +4. So again, that answer choice is wrong. It has it at +2. Third answer choice is NCl3. So chlorine is one that can have variable oxidation numbers, but really unless it's the central atom, you would expect it to be -1. So if it's in an ionic compound or if it's in a covalent compound but not the central atom, chlorine should be -1. We have 3 -1s, and that means we need a +3 on nitrogen. This has it at -3, so it's also wrong. And then finally for choice D, which is N2, remember the only time we have 0 oxidation numbers is when we have a neutral element, no charge associated with it. So in this case, nitrogen exists as N2 in its elemental form, but because it's a single element with no charge associated with it, the oxidation number should be 0. This one's wrong also. And so it always, psychs people out in exams is to pick choice E, which is none of the above. It does happen sometimes, so don't talk yourself out of it if you think that's the correct answer. But in this case, it was none of the above. So review the rules for oxidation numbers, but we will get some of that in the next few problems. But any quick questions on that before we tackle those? All right, so the last two problems, which also deal with oxidation numbers now, are going to be balancing redox equations, where again, redox equation being one that involves transferring electrons. And the people that put the test together, which I'm only tangentially involved with, like oxidation number questions. So there's going to be 2 of them, as I said. And they're both going to involve balancing equations. So we have this first one here. We have H plus MnO4 minus and NO as reactants forming Mn2 plus NO2 in water. We want to know what is the sum of all the coefficients. All right, so to do this, we have to be able to assign oxidation numbers. So let me write them out a little bit bigger so we can have room to do that. A little bit lower than that, too. Oh, geez, I gave you one of the coefficients already, so I'm getting ahead of myself. All right, forget I wrote that. Most of you probably zoned up on it anyway, so you didn't see that. So we have, those are the reactants, and the products are Mn2 plus NO2 and water. Now, the question came up a bit in class about redox equations. Do we have to know what the reactions and products are? The answer is no. We will give you all of the reactions and products that you need. You don't have to add any to this. So there may have been a stray homework question here or there that asked you to balance it in acidic or basic solution. You would have had to add either H plus or OH minus to do that, but don't worry about that for this test. If you need H plus or OH minus or water in the equation, we'll put it there for you. You just have to add the coefficient. So all we have to do in these problems is supply the coefficients. And these are hard to do by inspection because you have a lot of elements, a lot of charges in many cases. Both of those have to be balanced at the end. So we're going to use the oxidation number approach to do that. So we have to assign the oxidation numbers for all the elements first to figure out which ones are changing. H plus is an ion by itself, so it's going to have a +1 oxidation number. MnO4 minus, oxygen is -2. We have 4 -2s, which is -8. The sum has to equal the charge, which is -1, and so this becomes +7. Okay, so +7 for manganese, that's the highest that manganese will ever be. NO, simple binary compound, -2 for oxygen, +2 for nitrogen. Mn2 plus, ion by itself has to be +2, same as the charge. And then NO2 is another one, I think we saw this in the last problem. -2 still for oxygen in a covalent compound, which leaves a +4 for nitrogen to balance that. And then our old friend water, which I screwed up on 2, +1 -2. Okay? And water, we'll see it in a lot of these equations, so get used to writing +1 and -2 for water. Now we have to identify which oxidation numbers are changing. So we find that manganese goes from +7 to +2. Usually if you have a transition metal involved in a redox reaction, it will change its oxidation number. And then the other one that changes we see is nitrogen. It goes from +2 to +4. And so the reason we do this is we're going to add the coefficients for these 4 species first. MnO4 minus, Mn2 plus, NO and NO2, and we're going to add the coefficients in a way that allows the number of electrons transferred to be balanced between the two. So the number of electrons transferred is given by the difference in the oxidation numbers between reactants and products. Manganese starts as +7 and goes to +2, so that's going to be 5 electrons, a difference of 5. And then nitrogen goes from +2 to +4, which is a difference of 2, so that's going to be a 2 electron process. And what we need is we need to add coefficients to make sure that the number of electrons is the same for both of these pairs. So we have a 5 and a 2, so we want to find the least common multiple of those two. And so we take the 5 and we double it, that gives us 10 electrons. We take the 2 and we double it, multiply it by 5 to give us 10 electrons also. And so that means we're going to add coefficients of 2 in front of manganese, permanganate and manganese 2 plus, coefficients of 2 to ensure that that's a 10 electron process. And then because we had to multiply this by 5, that means we need coefficients of 5 in front of NO and NO2. Now once we set those coefficients, we don't want to touch them anymore because we've balanced the number of electrons, and anything that we do to those coefficients is going to throw those electrons off balance. So all that's left is to balance the oxygen and the hydrogen using the water and H plus that's left. That's what we do at the very end by inspection. So if we look at the left side of our equation, we have 8 plus 5 is 13 oxygens. On the right side we have 10. And so we're going to need to put a 3 in front of water to add 3 additional oxygen atoms to balance that out. And then by adding 3 waters, we have 6 hydrogens, and those come then from the 6 H pluses. So usually when you balance water and H plus at the end, balance water first and make sure that the oxygens work out. And then once you know how many waters you've added, you can go back and add the H plus to make sure that hydrogen balances. So those two, we just had to make sure that the number of elements on each side remain balanced. And so those are the coefficients. We need the sum for this problem. 6 plus 2 plus 5 plus 2 plus 5 plus 3, which I think is 23. Okay, so the correct answer would be A, 23. So as you can see from this problem, redox equations very often have large coefficients and a lot of coefficients, so trying to do this by inspection is probably not going to be a good strategy for you. So learn to use the oxidation number approach, and at the very least get the number of electrons balanced, because sometimes that's all the question asks you about is what coefficients involved with these, in which case you could even stop after balancing those. But that's the way we do the full equation, which we needed to do here to get all the coefficients. So questions on this one? All right, so the next one is pretty much identical, so if you think that makes sense, we can go through and do this. So we have, in this case, chromium chloride, nitric acid, making chromium nitrate, HNO2, water, and HCl. So a lot of different things here. So the first step, again, is to assign oxidation numbers. So in this case, we don't have any ions by themselves, but we do have ionic compounds. So chromium chloride is an ionic compound. In any ionic compound, chlorine is going to make a -1 anion. and that would also then be its oxidation number is -1. 2 -1 anions means that the metal in this case has a +2 charge. So transition metals are variable, so it's determined by the ions that are paired with it. So that's the oxidation numbers for chromium and chlorine. We have HNO3, which we've already seen before, which is going to be +1, -2, and then +5 for the nitrogen. So those are the oxidation numbers for HNO3. All right, and then on the product side, we have chromium nitrate with 3 nitrates. So that means the metal in this case is a +3 charge. So NO3- is just HNO3 with a lost proton. So the oxidation numbers for nitrogen and oxygen stay the same. They're not affected by losing a proton. So this still is -2, and this is still +5. We could have also worked that out separately by seeing that NO3- has a 1- charge. So if you have 3 oxygens at -2, you need a +5 on nitrogen. HNO2, +1 for hydrogen, -2 for oxygen. 2 -2s and a +1 is a -3, so we need a +3 on nitrogen to balance that. And then we have water and HCl, which are the easier of the two. So -2 and +1 for water, and then +1 and -1 for HCl. Okay? Remember, hydrogen pretty much always being +1, especially when it's in covalent compounds. All right, so those are the oxidation numbers. We have to find the ones that change. Now, the one thing we see here is that this is one of those problems like we had in class where we see that chromium is going from +2 to +3, so that's one of our changes here. That's a 1 electron process. And then we also have nitrogen going from +5 to +3 here, so that's 2 electrons. But we also notice that some of our nitrogen stays at +5. We have +5 for nitric acid. We also have a bunch of +5 nitrogens in our nitrate counterion. So this is where I like to then balance the nitric acid HNO3 in sort of 2 separate parts. So we know that we have to get the number of electrons balanced. So that means that this chromium chloride, we need to double the coefficient to make it also a 2 electron process. So that gets a 2 and that gets a 2. We don't need a coefficient on HNO2. It's already a 2 electron process. But then when we have HNO3, we know we're going to have to add some more of it. So we need 1 HNO3 to balance with the 1 HNO2 that's formed when we reduce that. But we also need additional HNO3 to make sure that we have enough nitrates present for the ionic compound that we're forming. So as I said, the way I like to do that is we're going to write a coefficient of 2 in front of chromium chloride. We have 1 HNO3 that we need to balance the electron transfer part. And then we're going to have a second pool of HNO3 that we're going to use to balance the atoms by inspection. And then on the product side, we saw that there's going to be a coefficient of 2 in front of chromium nitrate, which we won't change now because the number of electrons are balanced. A coefficient of 1 in front of HNO2. And then we have HCl and water, which we have to balance by inspection. Alright, so those are the reactants and products. Again, this one is already set. This one is already set. We just have to make sure that the number of oxygens and hydrogens are balanced. So if we look at our product here, we have 6 more nitrates that we need. 2 chromium nitrates, each with 3 NO3 minuses. So we need 6 more nitrogens. So that's going to come from there. And now we have to look at oxygen to balance water. So we see that these 6 nitrates are not losing any oxygen, but this one here that gets reduced to HNO2 is losing 1 oxygen. So we need 1 more water over here to balance that. And then to balance chlorine, we have two chlorines over here, so that 4, 2 times 2. So we need a 4 in front of HCl. So again, those last ones, you could do them in different orders. You can think about them different ways. Once we get this part up here done with the number of electrons, we just have to balance the rest by adding coefficients to make sure the atom is balanced as we normally would for any chemical equation. So that's the final set of coefficients, and we're looking for the sum of the coefficients on the reactant side, which are, now we would simplify this a little bit too, I suppose. We could write this out in a simpler way. We can take these 2 coefficients, a 1 and a 6, and combine them back into a single coefficient, 7 HNO3. Where again, 1 of those nitric acids is involved in the redox reaction. 6 of those are just involved in supplying counterions for the compound that we form. So that's the final form of this equation, but what we really need is the sum of the coefficients, 2 plus 7, which is 9. Sum of the coefficients on the reactant side is what we asked for here. All right, so that's another example. The only little twist here was the idea of having to balance HNO3 in 2 separate parts, because in some cases it was losing electrons, in other cases it wasn't. Gaining electrons, in other cases it wasn't. So we had to deal with that a little bit differently. All right, that takes us to the end. Any last questions before I wrap this up? All right, so I'll see you guys next week. I'll be around most of the day, Monday through Wednesday. So if you have any questions about your exam as you prepare for it, please come and find me.